Okay, so in the first paragraph, it is shown that we have some linear operator A and it will act to any state as follows. Suppose we have any state psi which can be decomposed to its eigenvalue spectrum as summation over n cn phi n, where n represent the states of the vectors. If n equal to 0, then it will be ground state, and so on. N equal to 1 first excited, n equal to 2 second excited, and so on. So we can always have this superposition principle in quantum mechanics. So as a property of a linear operator, it can acts on all the eigenstate, uh, or it is better to say that all the orthonormal basis states. Okay, as follows: Si is equal a cn phi n, and since it is a linear operator, it will work on it will operate on every eigen states possible. Okay, so now let's come to the matrix representation part. So we already know that completeness relation can be represented as sum over n, outer product of phi n is I, where phi n are the eigen basis of that Hilbert space, which we have assumed like this. Okay, so the curly h is represented by the Hilbert space notation. Okay, now let us have the let us have the operator A. So we can have this to be same like this, because this is nothing but the identity matrix. Okay, this is the identity matrix according to the completeness relation. Now we can relate this one to this one. How? Let us see. So this can be represented as this, and this can be, we can take another notation k because of the orthonormal condition. Okay, so phi k. Now we can take these two summations at one end. So this is nothing but phi n, nothing but phi n. This is a, this is phi k, this is phi k. Okay, now this is nothing but a number, since it is a inner product. Okay, it will act to this phi k state, giving some eigenvalue with the same eigenstate. Okay, so this will nothing but a satisfying the eigenvalue equation. Okay, in another words, we can also simplify this to sum over n cn a n phi n. Now you can understand that by operating a on phi n, it gives a n eigenvalue with phi n eigenstate. Okay, now this is a number, we can represent this as a n k because of n k notation. Okay, now since it is a number, we can take out of this sandwich case. Okay, and this is nothing but phi n, this is nothing but phi k. So this is the representation of a matrix form. Now how can we get these elements of the matrix? Okay, now let us see. Suppose we are considering some ith and jth term. So this, let us take this. Okay, so it is better to represent phi because we had already taken phi. So this is nothing but n, this is nothing but k, this is nothing but a n k, this is phi I, phi n, this is phi k. In operator, it is very essential that to which side we are applying it. Okay, the order is very important. So phi k, and this is phi j. Now what is this? Taking this summation n into the consideration, and this. So what is this? This will satisfy the orthonormal condition. So, and similarly this second sum also will satisfy the orthonormal condition. So this is nothing but a n k, this is sum, we are taking two sums together. Okay, and this is delta I n, delta k j. So the only value of n complete summation. When n equal to I, this will have some value 1, and k equal to j, this will have value 1. Otherwise, for all value of n and k, this delta term will vanish. So this is nothing but aij. So from this we have an idea that this phi n a phi k is a n k, which is the entry of nth row kth column element of a matrix. So if this is a matrix and this is the kth column, this is the nth row, so this is the nk term. So in other words, this is a00, a10, so on. This is a0n, an. Now in general, how we can represent a01 in computational basis? 0, a1. Now let us do some work. So in computational basis we have 0 is nothing but 1, 0, and 1, 0, 1. Okay, so what are the entries of sigma x matrix? So sigma x matrix can be represented in computational basis as 0, 0, 0, 1. This is 0, 1. So what is the entry of sigma 0, 0? 0 sigma x. Sigma x, no? Okay, 0. This will have to evaluate. Now the interesting thing about sigma x is that by applying sigma x on 1 we get 0, and by applying sigma x to 0 we have 1, like NOT gate in our electronics. So what is this? 0 sigma x 0. Now I will not going to write these things. Okay, so 0 sigma x 0. So sigma x operating on 0 will give 1, and 0 and 1 inner product is 0. So I am writing here sigma s is equal, first term will 0. What about the second term? This will 0 1 term, no? So 0 sigma x 1. What will be this? By applying sigma x on 1 we get 0, and 0 0 inner product is 1. This. What about the third term? This is 1 0. So this is 1 sigma x 0. So by applying sigma x on 0 we'll get 1, 1 1 inner product is 1. And similarly you will evaluate sigma x 1. Nothing to evaluate here. So sigma x operating on 1 will give 0, inner product of 0, and 1 is 0. So this is nothing about famous Pauli spin X matrix. Okay, so in this way we can construct the matrix element of any linear Hermitian operator belonging to some Hilbert space H. Thanks.